Start by asking a research question. What do you want to know? State your hypothesis. What do you think will happen? Explain your experiment. What data are you collecting, and what's your control? Analyze your results. What observations did you make? Make a conclusion. What did you learn? And do you have any more questions?
Letter T, the dark corners of statistical tests models.
Hi Stata,
Hi Amanda.
welcome to episode 2 from our Stata by Heart program.
Alright Amanda, I really need to learn statistics. What I know is a drop, and what I don't know is an ocean.
Yes, Stata, I see. Fear is the worst enemy of progress. There are things there that our little minds still don't comprehend. But don't worry, in the end, our educational program will strengthen our statistical knowledge.
I have no doubts. Yesterday learning, today learning, and tomorrow learning are connected in a strengthened circle of learning. In the end, everything is connected and we will succeed.
Well, let's enter the wormholes and go back in time to the hypothesis test era.
Oh, a true Einstein-Rosen bridge. Hope I can finally collect statistics.
Oh my, time passed by. Wow. Stata, we came here for a statistical test flashback, right?
Sure, Amanda. Let's do it.
Statistics test models era. Let us start explaining about the response variable and the explanatory variable. The response variable measures the outcomes of a research. It is a dependent variable, and the explanatory variable represents the changes in the response variable. It is the independent variable. Also, we classify the variables in categorical or quantitative data. The categorical data sets subjects in different groups, while quantitative data, which is the independent variable, it is the manipulated variable, the one that varies. It is the suspected variable of being the cause in a causal relationship or the predictor of another variable. The choice of a statistical test depends on the response variable and explanatory variable, as we can see in the figure. Now let us talk about the two sample t-test. First, the main assumptions are as follows. For instance, time that drug A total relieves pain after orthopedic surgery, time that drug B total relieves pain after orthopedic surgery. We will use a small sample size, 4 subjects in each group, to become easier to explain it. The statistical techniques have the form, the observed value is equal, mean response plus random error. So in group A, the subject 1 total relieves pain in 1 hour, subject 2 total relieves pain in 2 hours, subject 3 total relieves pain in 3 hours, subject 4 total relieves pain in 2 hours. In group B, subject 1 total relieves pain in 4 hours, subject 2 total relieves pain in 3 hours, subject 3 total relieves pain in 2 hours, subject 4 total relieves pain in 3 hours. Thus, The group A mean represents the mean time of hours that drug A total relieves pain, which is 2 hours, and group B means represents the mean time of hours that drug B total relieves pain, which is 3 hours. Let us look at this presentation. The observed value is the observed data response. The mean value is each group mean, and the random error is the difference between the observed value and each mean group. In reality, we have two unknown populations, and mean A represents the mean time of the mean number of hours that drug A totally relieve pain, and mean B represents the mean time of the mean number of hours that drug B totally relieve pain. We took a few samples of each of these populations to calculate the mean of group A and the mean of group B. And now we have the null hypothesis, which represents that the two drugs total relieve pain in the same mean of time, and the alternative hypothesis, which represents that the two drugs do not relieve pain in the same mean of time. Finally, in this hypothesis test, we cannot just look at the mean values to reject or fail to reject the null hypothesis, but we also have to look at the standard deviation, error term. The error term represents how far apart the points, subject's results, are from the overall mean value. Now let's talk about ANOVA. In ANOVA, the assumptions are as follows. In ANOVA test, we do not use the two groups' means. Here the mean response is broken in a grand mean and in two group effects, alpha A and alpha B, hence, the overall mean will be 2.5 hours. The effect size, alpha, is determined by the difference between each group mean and the overall mean. So alpha A will be the decrease of expected relief time pain in 0.5 hour, and alpha B will be the increase of expected relief time pain in 1.5 hour. Visually, the way we can think about this is that we have an overall grand mean, which is 2.5, and we measure the effect of group A, which is a decrease of 0.5 hours, and the effect of group B, which is an increase of 1.5 hours. In this example, when we think about the null hypothesis in ANOVA will be, is the effect of group A called the effect of group B. Thus, when we brought the hypothesis in ANOVA, we look at the effect size. Let us continue. Now talking about linear regression. Here the assumptions are as follows. In regression, we do not use the two groups' means. Here is done a model for a straight line, beta b, using y-intercept and the slope. Here we use the form. In this formula, I can be 0 or 1, and we use the x0 or x1 to indicate which group the data follow it. When x is equal 0, that will be the same as mean A, which is beta 0. And when x is equal 1, we can represent mean B as beta 0 plus beta 1. Thus, the null hypotheses when there are two groups will be mean A equal mean B, which indicates beta 1 equals 0. In other words, we test where the slope is equal to 0. Therefore, if the mean of the drug A is equal the mean of drug B, we expect to demonstrate that the slope is 0. The expected y-intercept is equivalent to the expected value when x is 0, and the slope is the change we expect in response when we go from x0 to x1. Visually, in regression we define drug A and drug B in x equals 0 and x equal 1. And we create a regression line to fit our data. If the mean of drug A is equal to the mean of drug B, we will expect the sample data to demonstrate that slope is 0.
Oh, look, Stata, the wormhole is open again. Let's go back quickly.
Right,
Come on. Oh, Stata, it's so nice to come back, don't you think?
Yes, Amanda. It sounds like everything repeating, that this has all happened before, like a massive deja vu.
That is what time travels looks like. But now, in this present time, the time is running out. We have a cumbersome statistical analysis, Adam. Professor Manetti wants to conduct a phase 2 multi-center, double-blind, randomized, placebo-controlled trial. The study aims to test a new opioid agonist drug to postoperative pain outpatients undergoing knee arthroscopy.
Oh, I remember it. And the P code is P. Outpatients undergoing knee arthroscopy. I. Postoperative analgesia using the new drug hourly plus standard analgesia therapy. The C is the postoperative analgesia using placebo plus standard analgesia therapy. The O is the sum of pain intensity measured using visual analog scale. And the T is the first 8 hours of postoperative.
The proposed sample size is 100 patients in 4 centers, Rio de Janeiro, Seattle, London, Milan, so each center will have 25 patients.
Here, the assumption of normality is guaranteed by the central limit theorem, but data transformation with log can be necessary if data shows skewed distribution.
Yes, Sarah. And our dependent variable is the sum of pain intensity measured using visual analog scale VAS, a continuous rating scale.
And the independent variable is the group active drug versus placebo.
So what can we do now, Sarah? Let's think about the research question first. What is it?
Yes, well, let's see. Does the addition of the new drug to standard analgesic therapy reduce the sum of pain intensity in the first 8 hours of postoperative treatment in outpatients who undergo a knee arthroscopy when compared to control?
Yeah. So we have a sample random to be divided in 2 groups, active group versus placebo. The outcome is the sum of pain in 8 hours after surgery, based by previous studies that showed that the peak of post-surgical pain is within first 8 hours, and the patients will report their pain intensity using a visual analog scale from 0 to 10. Let's do an overview, Sarah. We have 2 groups and we have a continuous dependent variable, which is our outcome. It seems that we will not have any issue regarding the normal distribution of data. And let's say that we do not have any problems with the other model assumptions for t-test. So here our alternative hypothesis is, does the sum of pain intensity in 8 hours after knee arthroscopy is reduced in patients using active drug plus standard analgesia versus control? Well, the big pro here is that the t-test is strong enough to support some degree of non-normality, and the primary endpoint is as simple as it can be. But Sada, I was wondering, we can also think about another research question such as, does the addition of the new drug to standard analgesia reduce sum of pain intensity at different postoperative time points every hour until 8 hours in outpatients who undergo a knee arthroscopy surgery when compared to control?
Very good, Amanda. Let's talk about repeated measures ANOVA model. As you said, we don't have problems with normality. The dependent variable, our outcome, is still continuous, measured pain intensity using visual analog scale in intervals of 1 hour up to 8 hours for 2 groups, time versus group interaction effects.
Here, Sarah, we must emphasize that we have 3 groups. Our independent variables are the group, 2 levels, placebo versus active drug, and the time, 8 levels, 1 up 8 hours. The alternative hypothesis is to evaluate if time versus group interaction effect is significant. But why ANOVA, Sarah?
Well, because the outcome assessed by t-test may not encompass the effect of the new drug. For example, we need to mitigate the placebo effect that mostly occurs within 2 and 3 hours after surgery. Thus, pain intensity should be repeatedly assessed every hour in the first 8 hours after surgery. However, a post-hoc statistical test will be required to check comparisons between active versus placebo.
However, Sarah, the ANOVA does not tell us where the difference lies.
Correctly, Amanda. A post-hoc statistical test will be required to check comparison between active drug versus placebo at different time levels. This statistical test can weaken the study power in cases of factors with several levels, which leads to multiple post-hoc comparisons, hence increasing T1 and T2 errors. Oh, I have another research question, Amanda.
Wow, tell me please.
Well, does the addition of the new drug to standard analgesia reduce the sum of pain intensity at different centers in the first 8 hours of postoperative in outpatients who undergo knee arthroscopy when compared to control?
Good question, Sarah. So here, our outcome is to evaluate the sum of pain in 8 hours after the procedure and also to access confounders, right?
Right, we can access covariates such as center and age.
I see. So for this research question, the most proper study option, study 2, is the linear regression to control for relevant covariates, such as ANCOVA.
You did well, Amanda.
But Sarah and Amanda, there is a drawback. ANCOVA decreases the power of the study, though, to control for center and age diminish the variances so increase the strongness of study.
Oh, it reminds me a quote. The end, such as statistical test choice, is the beginning, such as the pickled, the research question, and the beginning is the end. So, the choice of statistical test depends on the research question.
For sure, Sarah. Very, very good point. But how can we choose?
Well, I'm feeling the butterfly effect. A small variation that seems insignificant can generate enormous change over time.
Oh, this would be an even more chaotic discussion.
Yes, but in daily life, the butterfly effect serves to let us know the limit of our knowledge. So, let's give our humble opinion. Well, we have a sample size which can allow balanced groups.
Sure, and I believe that reducing the sum of pain intensity in the first 8 hours is practicable and relevant enough to test this new drug in this new situation, postoperative knee arthroscopy, in order to achieve the desirable efficacy.
Yes, in this way, unpaired t-test is simple to perform. It measures a relevant and simple outcome. It is powerful and even supports some degree of non-normality.
Oh, the wormhole opened again.
Yes, let's go inside again.
Again. Oh,
I'm going.
no, I'm going to save you. Well, Sada, we are back into this area, and what's the answer? T or not to T?
Therefore, the answer is let it be.
When I have come to dependent variables, Professor Freddy comes to me, speaking words of wisdom, trying to be between groups means my darkness. Professor gets standing right in front of me. Check for all assumptions, he said. Let it be, let it be, let it be, let it be, let it be. Meeting all assumptions, let it be. And when there's certain evidence, I will rely on parity who agree. There will be an answer. For good it may be parted, there's still a chance for parity. We're in many groups, parity. Let it be, let it be, let it be, yeah, let it be. There will be an answer, let it be. Let it be, let it be, let it be, yeah, let it be. Checking for assumption, let it be. There's still a light that shines on me. Do shop your own tomorrow, let it be. I wake up looking for eternity. Everyone come rescue me. For me, come where else, let it be. Let it be, let it be, let it be, yeah, let it be. There will be an answer, let it be. Let it be, let it be, let it be, yeah, let it be. Whisper words of wisdom, God's not me.